This is the video on Newton's first law. So the first thing that we did was we took a test on like just an initial response, because right now we're starting Newton's laws and it's called Aristotelian or Newtonian. So the idea is that we would take a quiz on 18 different problems and just see, well, how do you think right now, right? So if you were to get 0 to 5 correct, like you're thinking like Aristotle, like those ancient Greeks. 6 to 13, well, now you're thinking a little bit better, just like Galileo. And 14 to 17, you're thinking like a Newtonian, right? You are in the modern age of science. And if you get 18, then I just call you an Einsteinian, because you have just a deep understanding of how objects interact with each other. So that test was to determine, like, it was supposed to be pretty low because it's just based on your observations. So, like, determine how you think. Like, were you more close to Aristotle or closer to Isaac Newton? So, Aristotle versus Isaac Newton. So, Aristotle was a famous Greek philosopher that lived in the 3rd century BC. Now, his thought process was that forces keep things moving, that the only natural motion of objects was rest. Now, Isaac Newton came along, and his thought process was that forces accelerate objects and that rest and constant velocity are both natural motions for objects. Both of these brilliant thinkers had competing ideas on the motion of objects. However, they both agreed on ideas on the motion of objects as well. So if we look at Aristotle, right, just the way Aristotle thinks is based on casual observations, life experiences, logical deductions from given premises. That's why most people think like Aristotle. So this is how he viewed the world and why you probably think this way as well. Now, keep in mind, science operates under the principle of wrongness, and a lot of what he thought has now been proven wrong. So this is what the ancient Greeks and Aristotle thought. The state of rest is the only natural state of objects. Objects at rest want to remain at rest. To get an object to move, you have to force it against or to move against its nature. This was called forced motion. All bodies in motion eventually come to rest because that is their natural state. Thus, to keep something moving, you must continually apply a force to it. Objects fall or rise because they want to return to their natural state of rest in their natural place. This was called natural motion. Heavier objects have a greater tendency to want to return to their natural state of rest, so they fall faster. So heavier objects fall faster. All natural motion on Earth is straight lined, and all motion in the heavens and outer space is curved. So, based on observations around us, this is probably what you would come to as well. Now, there were some problems with Aristotle's ideas. Are forces necessary to keep things moving? Do horizontal projected objects move forward only because air pushes them forward and then fall straight down due to their natural motion? Or do they maintain their horizontal motion while falling in a parabolic fashion? And do all bodies fall according to the weight, or do all bodies fall at the same rate? So now enter Galileo, who, while he agreed with Aristotle that rest is a perfectly natural state for a body to be in, it is not the only natural state. He proposed that motion is just as natural a state as long as its motion is constant and in a straight line. So Galileo conducted this experiment that shows that constant velocity was a natural state of motion. He made 2 ramps and rolled a ball down each. He noticed that as he reduced friction by sanding that ramp, the ball would get closer to that original height. He proposed that the ball could not go any higher than the original height. He also proposed that if he were to bend one of the ends of the frictionless ramp completely horizontal, the ball would continue at a constant velocity forever, or until something stopped it, because it was not able to return to its original height. And you can see that in that little graphic here. He said, well, if this is frictionless and it can't return to its original height, if I bend it all the way down, it's just going to continue going in a constant motion forever until something stops it. So essentially, his experiment showed that constant straight line motion was just as natural as at rest. Aristotle got it wrong when he assumed that rest was the only natural state of motion. If a body changes its motion, then there had to be some cause, some force to change its motion, according to Galileo. With this idea, Galileo first came up with the concept of inertia. In other words, a body has the tendency to keep doing what it is already doing. If it is at rest, it has the tendency to stay at rest. If it is in motion at a constant speed in a straight line, then it has the tendency to keep moving at that same speed in that direction forever. So just think about the Voyager probes, like the Voyager 2 out in space. It is traveling at 15 kilometers per second, and with nothing to slow it down, it will continue forever at that speed in that direction. So once you get into space, once you remove like the air friction and like the gravity is negligible, it'll just keep going. There's nothing propelling like pushing these Voyager probes forward. It's just that inertia. It has the tendency to continue what it's doing. So if we already learned about mass versus weight, and mass is closely related to inertia. So what caused these rocks to move? So if we look at these mysterious moving rocks, right, just asking this question indicates that we believe there must be a cause for this motion. Now, could the cause of the mysterious and moving rocks be by somebody pushing it? Yes, Aristotle would have said yes, and so would Galileo. They might have disagreed on the natural state of objects. However, they both agreed that something has to push these rocks. Neither of them had observed objects spontaneously going from rest to moving without a cause for that motion. So what do you think caused these rocks to move? Well, if you watch a video or you do a little research on it, it's just the perfect weather conditions causes a little layer of ice, and then as that ice melts, if there's a wind, it'll drag those rocks, and it'll make like this dragging motion. So later in the 17th century, Newton came along and took the ideas that Galileo proposed and furthered them. He then expressed them in 3 distinct laws. We know them now as Newton's laws of motion. Now, you've probably heard them, even memorized them, but now we're going to explore what they mean. So inertia. Inertia is a property of all material bodies to resist a change in their motion. Even though inertia is just a made-up word, we can still measure the amount of inertia a body possesses by measuring its resistance to acceleration under an applied force. We define mass as a measure of the amount of inertia that a body possesses. Now, all of you can probably say Newton's first law. An object at rest will stay at rest. An object in motion will stay in motion unless acted upon by an unbalanced force. So it's just a testament to how you can memorize things, but I want you to fully understand them. Newton's first law of motion is also known as the law of inertia. And it states objects at rest remain at rest, and objects in motion remain in motion in a straight line unless acted upon by an unbalanced force. Great. You probably know this. You've probably heard this before, but what does it mean? So this is a new way that you could look at Newton's first law, but a bit more mathematical. Now, the symbol used to represent net force is that, right? So it's net force. Now, as you hopefully remember, net forces produce change in motion, acceleration. So therefore, another way to state Newton's first law of motion is net force implies acceleration. So net force is implied to a body, then that body will accelerate. If a body accelerates, then there must be a net force applied to it. Those two go hand in hand. Net force implies acceleration. Acceleration implies a net force. Both the state of rest and constant velocity are natural. Acceleration is the only real motion. It requires no force to keep something moving at a constant speed in a straight line. And if an object changes its motion, so it speeds up, slows down, or changes direction, then an unbalanced force must have been applied to it. So I said this slide comes up a lot when you're learning like Newtonian physics. Well, balanced forces, the net force is going to be 0 newtons. That object is at rest or at a constant velocity in a straight line. Unbalanced forces, all the forces do not cancel out. The net force is not 0 newtons, and the object will be accelerating, right? The object will be accelerating. So according to the theory of special relativity, in physics terms, there is no difference between being at rest and moving at a constant velocity. Acceleration is the only real motion, the only absolute motion. So, and there are 3 ways to accelerate. You speed up, you can slow down, or you can turn. So to understand the concept of inertia, we did this lab. It's called Shake It. So there's one bottle that's empty, one bottle that's full. So grab both the empty and the full bottles by their necks, invert them, and then shake them back and forth. What is resisting the force of you shaking the bottle? Inertia or weight? It's going to be the inertia, right? Because you're shaking them back and forth. You're feeling that resistance to change in motion. It's moving one way, then you stop it and move the other. You stop it, move it the other way. That's what's resisting it. It has mass. It has inertia, which means it has mass, which means you are feeling that resistance. Now, if you lay the bottle horizontally and then you flick them off the table, you flick them with your finger, what is resisting it? What is resisting the force of you flicking the bottle? Inertia or weight? It's going to be the inertia again, right? Weight is pulling down. Gravity is pulling down. You're flicking it horizontally. So you feel that because it's at rest, you have to accelerate it to get it moving. Now, just simply holding the bottles out in your hand without trying to accelerate them or change their motion, you're feeling that weight pulling down. Now, if we were to lower the gravity, like let's just say we took this and we did this experiment on the moon where the gravity is 1/6 that of Earth, How would the experiments of shaking, flicking, and holding the bottles change or not change? Well, the first two experiments would not change, right? Shaking the bottles, you would still feel that same resistance, right? You would still feel the inertia. It's resistance to change in motion. If you were to if like even flicking them, getting them to accelerate would still you'd still feel that resistance as you flick the bottles across the table. And holding them though, that would get a little bit easier because that one with sand would feel a little bit lighter. Now, if you perform this experiment on the ISS where there is no like apparent gravity, how would the experiments of shaking, flicking, and holding the bottles change or not change? So shaking and flicking the bottle, that would not change. You would still feel that same resistance. You would still feel the same resistance, but holding them, you could not hold them. You do not feel that weight. So that's the difference between inertia and weight. So now let's ask this question. What is the best strategy for escape when being chased by an alligator? So an alligator can run 20 miles per hour. An average human can run 15 miles per hour. An alligator has an average mass of 225 kilograms. The average human has a mass of 62 kilograms. So an alligator has a larger mass than you, meaning it has more inertia. Now, do you think it would be easier or harder for it to turn? Well, think about it this way. If you had to turn quickly while pushing a shopping cart, would it be easier or harder if it were full? Well, it would be a lot harder to turn while it's full. So the alligator may be faster, but you would be able to turn quicker, run away in a zigzag motion, and you'd be able to get away with nothing but an interesting story. So the idea is that like it when it's changing its motion, it has more mass, which means it resists that change in motion more. But you have less inertia. You have less mass than an alligator, so you should be able to turn a lot quicker. Now, with alligators, they're not just going to sprint after you. Usually, if you survive that first strike, you can get away. Now, if larger predators, they have different rules. Don't use this as a go-to. Like bears, some of them you're supposed to back away slowly, make yourself bigger. Make noise as you're walking, so you skirt away. You don't want to run away from a bear, but if it's charging and it's an absolute last resort, bears have a lot more mass than you, so it would be a lot harder for it to turn. But like I said, don't run away from bears, right? Now, why is it hard to drink water in an accelerating car? So if you're a passenger in a car at rest, the driver slams on the accelerator, what does your body do? So it feels like you're moving backwards. You're a passenger in a car going 30 miles per hour, the driver slams on the brake, it feels like you're moving forward. Now, you're a passenger in a car going 30 miles per hour again, and it turns sharply to the right. So it feels like you're getting pushed to the left. Now, think about all these cases. What are the accelerator, brakes, and steering wheel applying the force to? They're applying that force to the car. That car is moving forward. The car is stopping. The car is turning, but it's not applying the force to you. So in all these scenarios, the car is accelerating around you. You have inertia and resisting that motion. If you're sitting at a stoplight at rest, if you're holding a cup of water, the same thing happens. Everything around that water is accelerating, and that water has inertia, which means it resists that change in motion. So you would accelerate into that cup of water. Same thing if you're sitting at rest and they slam on the gas, it feels like you're flying backwards, like something's pushing you backwards. But what's really happening is that car is accelerating forward. You are at rest, and you do not move forward until the back of the seat pushes you forward. So in order to explore this a little bit more with water, we did the inertia simulation. So when you first place the cup down, you'll see that it is at rest. You can manipulate the free body diagram to get the free body diagram. Use Newton's first law to explain what the water level looks like. It's going to look like this because there is not a net force being applied to anything. You have a gravity, you have the normal force. Now, once we apply 500 newtons to it, it's going to start to accelerate. Well, why does the water level look like this? And I give you a hint. Is there a net force being applied? Yes, there is. But what is it being applied to? It's being applied to that cup. It's not being applied to the water. So yes, this is what my free body diagram is. I see I have an unbalanced force. So what's happening is, well, that water is not being pushed back against the cup. What's happening is that cup is accelerating around the water, and then eventually the back of the cup is going to push it forward. Now, after it gets up to 40 meters per second, he lets go of it. And well, now there's not a net force being applied to it. It's going at a constant velocity. So the water level is going to be level. It's going to be horizontal, right? There's only a gravity and a normal force. There's no acceleration here. Now, if you could, this last one, now we're going to push it in the opposite direction. We're going to slow that glass down. That's what the water level is going to look like. Now, using Newton's first law, explain why the water level looks the way it does. Well, that water has inertia. It's moving forward. It has the tendency to continue moving forward. Now, this person is applying a net force to the cup, not the water. So the cup is like slowing down. The water doesn't, and it's going to be and it moves forward to the other side of the cup, and it looks like that because the cup is pushing it in the opposite direction. It's slowing it down. So if we look at the water levels in the cup in all four scenarios, which of those cups is the water not level? It's going to be the one where they're accelerating, right? Where there's a net force. And the reason why the water level looks that way is because the net force is being applied to the cup, not the water. So how much confidence do you have in the laws of physics? So if you take a cup of water and you spin it around fast enough, the water does not come out. Think about the tendency of the water. Where does that water have the tendency to go? The water has the tendency to travel in a straight line. The water is resisting that change in motion. Now, what is happening to that water? The water is traveling in a straight line, and the cup is providing an inward force, keeping that water in a cup. Think about being in a car that is turning really quickly. It feels like you're being pushed against the side, but you are not. You are just continuing forward, and that car is turning around you, and eventually that car door is pushing you the opposite. That's exactly what's happening here. Exactly what's happening. All right. So how can inertia be used to impress your friends? So this is the tablecloth trick. So in this tablecloth trick, you can see that there. This is just a funny video. What is the person applying that force to? What isn't it being applied to? The person is applying a force to the tablecloth. The dishes on the tablecloth have inertia and are at rest. They have the tendency to stay at rest. As the tablecloth is sliding, there's a small kinetic friction force, but it happens so quickly, it's not enough to pull the dishes off the table. So we did the card, coin, cup lab, which we did this, where you were to put a nickel on top of the card, you flick the card. Explain why you observe this. So what happened is that the card goes out and the coin falls in. Well, same concept. What are you applying a force to? You're applying a force to the card. What aren't you applying a force to? You're not applying it to the coin. So that coin has inertia. It's at rest. It has the tendency to stay at rest. So if you don't apply a force to it, it's not going to accelerate. So if we look at the next one, these are the different free body diagrams for the different scenarios, one where it's on the card, one where the card's moving, and one where the card is out. So we're looking at the coin. Notice if we ignore friction, that coin should be at rest because those forces are balanced. The last questions, repeat the experiment with a penny, then a quarter. Did changing the mass of the coin affect how difficult it was to get into the cup? Explain your answer. Use the word inertia. So I give you a hint there. Is there a net force being applied? If so, what is it being applied to? It's being applied to the card. It's not being applied to the coin. It should not matter what the mass is on top of there because they have inertia. They are at rest. They have the tendency to stay at rest. If you do not apply a net force on it, it's going to continue to do what it's doing and staying at rest. So it should not matter what coin you put on top of there. How can inertia be used to hold a marble in a wine glass upside down? So this is the wine glass challenge. So in this, what you're going to do is you're going to spin the wine glass around until you can pick up that marble and hold it upside down for a little bit and flip it over. So this is the challenge. Pick up the marble off the table without touching the marble with anything other than the glass. Keep the glass upside down with the marble in it for 10 seconds. Then rotate the glass right side up and set the glass on the table with the marble still in the glass. So there are two natural states of motion. If the marble is in motion, what does the marble have the tendency to do? It wants to continue in a motion. What must act upon the marble and for it to change? So it's an unbalanced force. What forces are being applied to the marble when it is spinning in the glass while the glass is upside down? Is the marble accelerating? Will the net force be equal to zero, not zero? Are the forces balanced or unbalanced? A lot of different examples here, but gravity and that glass is applying a force. The marble is accelerating because it is turning. So that means the net force is going to be not zero and the forces are going to be unbalanced. Now, this last part is using Newton's first law to explain why the marble stays in the glass while it is spinning, even though the glass is upside down. So even though it's upside down, what's happening is that because it's curved, it's spinning fast enough, it has the tendency to continue in a straight line, But what's happening is that glass is always providing that unbalanced force inward and upward to keep it in the cup as long as it's moving fast enough. And basically what that means is that once that upward force is larger than gravity, then it will be able to stay in the cup. So how can inertia be used to determine if an egg is hard-boiled or raw? That brings us to the excellent challenge. So this is the excellent challenge. The challenge: there will be 2 eggs on a table. Without cracking the eggs, shaking the eggs, or picking the eggs up off the table, determine which egg is hard-boiled and which egg is raw. You should be so confident in your choice, you should be able to crack your choice for the hard-boiled egg over your head without fear. So gently put one of the eggs on the table and spin it. While it is spinning, gently put your finger on top of the egg for half a second to bring it to a stop. Then immediately pull your finger away. Repeat this process with the other egg. What do you observe? Was there a difference in how the eggs react when they were stopped? Write your observations. And then explain what you observed. Based on what you've observed, how could you tell which egg is hard boiled and which egg is raw? And I give you a hint there. Is there a net force being applied to? If so, what is it being applied to? And then I say you should be able to crack your choice over your head that you're so confident. Well, what happens is that you are applying, when it's spinning on the table, you're applying a force to the shell, not what's inside of the shell. So the one that's raw, what's inside the egg, should continue spinning after you stop it, and it'll continue spinning. The hard-boiled one will just stop because the insides are solidified and they're not moving around. If you perform this experiment on the International Space Station where the eggs will be weightless, would this challenge be harder, easier, or just as difficult? Explain your answer. The answer is it would be just as difficult, right? Because you could spin an egg, and once you stop it, well, you're stopping that inertia, right? You're not stopping. You're stopping its motion, because what's resisting you is the inertia, right? It's not the weight. That's it's resisting that inertia. So once again, there is too much unknown in the universe to take a break from learning. Get out there and question everything.